Hi guys, in the last video we looked at explaining the components of the Laplace transform, the integral of the Laplace transform. Now we're going to look at, looking at the tables, Laplace tables. We're going to evaluate a few of them. And then the last thing we're going to do is look at the derivative property as taking the Laplace of a derivative. So let's get to work. The table of Laplace transforms is the tool that helps us. Recall what we spoke about in the last video. The Laplace transform takes x as a function of time and maps it to capital letter as a function of s. So this is a function of time. This is a function of the complex variable, the frequency domain is a frequency function. All right, and the tool that helps us do that is the Laplace transform. So that's f of t times e to the negative st dt from 0 to infinity. So that's the Laplace of f of t. Okay, so what we really do as we solve questions like this is we have a table of Laplace transforms. Okay, that looks something like this. You have a function on the left, f of t, and you get the Laplace on the right. So going from f of t to capital F of s is taking the Laplace transform. Going from f of s to f of t is taking the inverse Laplace transform. So it's as simple as that. You're moving from time to frequency, frequency to time. So usually you won't have to keep evaluating the integral the way you may think we have to do. These tools are very helpful. So you see you have u of t here being 1 over s, t of t being 1 over s squared, e to the negative at equals bt, and this. So they're really helpful tools to help us evaluate the Laplace transforms. So now we're going to solve a couple of them. We're not going to do everything, just solve a couple of them to see how they came about, then look at the derivative property. The first one on our plates, okay, is the Laplace transform of 1. So that means we're taking the Laplace of f of t. That means f of t is equal to 1. Okay, Laplace of f of t is 0 to infinity, e to the negative st, f of t dt. Alright, I'll just keep writing this, but I'll stop eventually, just so we stay familiar with the expression. So let's get to work. Now this is our function of time. So solving this, we're going to set up our integral from 0 to infinity. Our function is 1 times e to the negative st dt. We know we're multiplying by 1, so it's essentially the same thing. From 0 to infinity, e to the negative st dt. How do we solve integrals to infinity? So what we do is that we solve infinity for a number n, and then take the limit as n tends to infinity. That's how it's done professionally. Okay, but it's still the same thing. If you can picture taking the limit to infinity, you wouldn't have to do that. So let's just get to work. Taking the integral of e to the negative st is going to be 1 over the derivative of the exponent. We got e to the minus st. This is your exponential. Differentiating this is going to give you minus s. Dividing this, taking the reciprocal of this is going to be minus 1 over s. So this is going to multiply our original function. That's how you take the integral of exponents. Okay, so let's get to work. That's going to be negative 1 over s, e to the minus st, and we're going to take our limits from 0 to infinity. Okay, this is our upper bound, this is our lower bound. We sub this upper bound in for t, then subtract it from subbing in the lower bound. Let's get to, that's going to equal to minus 1 over s, e to the minus t, minus st, subtracted from negative 1 over s, e to the minus st. But t is going to be 0. Here t is infinity. So if you look at it here, we have e to the negative st. Okay, e to the minus st. We got minus s times t as t tends to infinity. So this is a really large number, and taking e to the negative st is the same as 1 over e to the st. If we let t tends to infinity, this entire reciprocal fraction is going to tend to 0. So the condition we usually keep here when taking the Laplace is that s is greater than 0. Or if you want to be more specific, the real part of s should be greater than 0. But this is usually always assumed. There's no need to do that. So we have e to the negative s times infinity, in a sense. That's 0. Okay? E to the minus s times 0. So e to the 0, this entire thing is going to go to 0. So e to the 0 is going to be 1. Okay? This is going to tend to 1. So this is going to be end up with minus 1 over s. It's the same simple trick. 0 minus 1 over s, if that's not clear. Minus 1 over s. So to summarize, we have the Laplace of 1 is going to be 1 over s. Simple and short. Let's get a move on. It's really fun. The second one we're going to do is e to the minus at. So, you know how we do, set up our integral, 0 to infinity, e to the minus at, e to the minus st dt. We've got the same base here, e and e, so that means we can add the exponents. Okay, so that's going to be 0 to infinity, e to the minus at minus st dt. We're going to factor out minus 1, and we're going to factor out time. Okay, so that's going to be still within the integral, 0 to infinity, e to the minus. Since you're factoring out minus 1, and both of these guys are minus, it becomes a plus inside the brackets. So minus s plus a multiplied by time. Okay, don't panic. This is the exact same thing we have here. Minus s minus a minus st minus at is the same thing multiplied by dt. Recall what we did for evaluating our limit, our integral to infinity. So that's going to be negative 1 over s plus a, e to the minus s plus a, this is in brackets, times time. Okay, and this is, this is not from 0 to infinity, it's not indefinite, it's a definite integral. So from 0 to infinity, we sub in infinity, take the limit, sub in 0, take the limit. That's going to give us minus 1 over s plus a, e to the minus s plus a t, minus 1 over s plus a, e to the negative s plus a t tends to 0 here. Okay, what can we see from here? This is like almost exactly the same identity we have for here, just at this time we've got to make sure s plus a has to be greater than 0. So when we're doing minus s plus a times infinity sort of, we still end up with a negative sign. If this is less than 0, then it will be minus s plus a, then minus a minus sign. Okay, this will be plus, and that will ruin the whole integral. That's what we mean when we try to define those limits. But I don't think you have to bother with them. It's just to make sure our understanding is a bit solid. So this entire thing is going to tend to 0. Okay, because you have e times minus a number, and n is tending to infinity, so that's going to go really fast. Taking the reciprocal of that, e to the n is also going to go very fast to 0. So this is going to 0. We have e times t, e raised to power 0. Record 0 is subbing for t here, so that's going to go to 0. So we're just going to end up with minus 1 over s plus a, which is simple and short, 1 over s plus a. Let's write this out clearly. So the Laplace transform of e to the minus at is going to be 1 over s plus a. Let's put a nice little box around that. Simple, short, and straightforward. Note, however, if you are now to find the Laplace of e to the at, okay, it is going to be 1 over s minus a. Okay, because the signs are being switched. Where's my mouse? Okay, third one we're solving for. Oof, how does that keep happening? Third one we're solving for is the Laplace of t. Okay, so that means this t is our function f of t. And to do this, we're just going to throw t into our integral. Okay, finding the Laplace of this guy. 0 to infinity, e to the minus, let's start with t, e to the minus st dt. What we're going to do here is a really fancy trick called partial fractions. Okay, you know how partial fractions work. If you were to find the integral of u dv around, okay, dv is going to be uv minus integral of v du Okay, these are inside. These are inside the bracket. So that's the two we're going to do here. So to make this work, we're going to define what's going to be our u, and we're going to define what's going to be our dv. So for this case, we're going to let u equals t. Then du is going to equal 1 dt. Simple and straightforward. We're going to let dv equal everything else in the integral. That's e to the, okay, let me give it a bit more space. So dv is going to be e to the negative, dv is going to be e to the minus st dt. Okay, that's everything left in the integral. V is going to be the integral of that. And we've done e to the negative st before. Negative 1 over s. Right? E to the minus, yeah, that's correct. E to the minus st. Throw these guys in. Let's substitute and have a house party. Alright, so that's going to be uv, u times v. So that's negative t over s. E to the minus st. We're still going to take the limits of this from infinity to 0. Then subtract integral of v du. Okay, so from 0 to infinity, what's our v? Minus 1 over s e to the minus st. And du is dt. So that's minus 1 over s e to the minus st dt. So let's evaluate this first half, okay? Let's get that out of the way first. We're trying to work out minus t over s e to the minus st from infinity to 0, okay? So, you solve in infinity first as n tends to infinity. So that's minus n over s e to the minus s n as, tends to infinity. Then subtract that from minus 0 over s e to the minus s times 0. Okay? This is obviously going to 0. You're literally multiplying by 0. So for this part, okay, you have minus n over s e to the minus sn. We're using n as a placeholder since n is going to infinity. It's the same thing mathematically. So what's going to happen is that we have e to the minus percent. Okay? This is going to grow much, much faster than this. Okay? E to the minus percent is going to grow much faster than this. So this whole part at the beginning is also going to tend to 0. I hope I made myself clear. We have minus n over s e to the minus sn. We're taking the limit as n tends to infinity. We have this. Okay, is there anything else to write? Okay, so we've practically got minus n over e to the sn, times s. Okay, this is going to go to 0. One of our infinity is going to go to 0 practically, because that's e to the minus sn. That's going to go very fast. That means you can clean this up. So that means we're not going to use this first part. Okay, all we're left with is this minus sign, then our integral. So we can do that simple and short. So that means we can bring out minus 1 over s. Okay, bring out minus 1 over s. So that's minus, integrating from 0 to infinity, 1 over s e to the minus st dt. We have done this before. That's going to be minus 1 over s. Oh no, it's plus. Okay, since we brought out the minus sign. Okay, so that's plus 1 over s multiplied by 1 over s. We just did this. So that's going to give us 1 over s squared. So therefore, the Laplace transform of t, that's time, is going to be 1 over s squared. No, you don't really have to do this. I'm just doing this to see that, okay, there are real ways these people arrived at the Laplace transform for these certain functions, and they didn't just come up with it. So you are encouraged to use the tables. You won't have to do this, or doing this often lets us have a strong practical understanding, a strong math foundation of, okay, this is how these guys did whatever it is they did to end up with what they got. Last one, this is second to last, I think. Sine omega t. Wow. How we do this? Okay, so we're going to use the Euler function for sine. Okay, so that's going to be sine. Is there no space here? Ooh. Okay, so that's sine omega t is equal to 1 over 2j. J is our complex number for electrical engineering. E to the j omega minus e to the minus j omega. Okay, so this is our like super tool that's going to help us solve this integral. You can check it with your calculator. This is how you write trig functions exponentially. So let's get to work. Throwing this right into our Laplace transform. So that's going to be, from 0 to infinity. Throw this guy back in 1 over 2j e to the minus j omega minus e to the, okay, this plus minus j omega multiplied by e to the, e to the minus st. This is j omega t. Okay, since we're finding the j omega t, since we're finding, sine of omega t. Okay. J omega t times e to the negative st. Alright. How does that work? Boom. 1 over 2j, let's bring out the constant. 1 over 2j from 0 to infinity. We're going to add the exponent e to the j omega t minus st minus e to the minus j omega t minus st, all with respect to time. So we're now going to factor out the minus sign, factor out time, okay? So that's going to be 1 over 2j from 0 to infinity e to the minus 1. That's going to be s minus j omega for the first one, multiplied by time, minus e to the minus is s plus j omega, multiplied by time dt. Alright, pretty amazing stuff. We've seen this formula before. E to the minus at is 1 over s plus a. We don't have to do much about that. Throw this back in. Okay, so that's going to give us 1 over 2j. 1 over 2j, open the bracket. 1 over s plus s minus j omega. Okay, that's the first. J omega e to the negative j omega t subtracted from 1 over s plus j omega e to the negative s plus j omega t. Alright, then we're working from 0 to infinity. How do we do that? This is the really fun part, taking the limits. So for infinity, okay, we're going to do this whole thing as it tends to infinity. How does that work? This is e to the negative s minus j omega times t. T is going to tend to infinity. This e to the negative e to the minus j omega is going to tend to 0. If your exponent is growing, if you have e to the a, and your a goes to infinity, okay, e to the a is going to grow to infinity faster than a. If you have e to the negative a, and a grows to infinity, e to the negative a is going to grow very fast to 0. It's simple. It's simple indices, okay? So let's get to work. That means that this entire first part of our function, the first half where we solve in infinity in, is going to disappear. It's going to go to 0. Because this is going to be, no, let me write it. Okay, so that's going to be n. I'm going to solve in n, and n is going to grow really, really fast. So that's 1 over 2j. Okay, let's just bring 1 over 2j out of everything. Really, really big. 1 over s minus j omega e to the minus s minus j omega n minus 1 over s plus j omega e to the negative s plus j omega n. Okay, this is where our limit as n goes to infinity. This goes to 0. We've established that. This goes to 0. We've established that. So this entire first part of our function is going to go to, we're going to go to 0. Okay, this is in the biggest bracket. Okay, then subtract. Then we sub 0 in. Okay, sub 0. Alright, so that's minus 1 over s minus j omega e to the 0 is going to go to 1 minus 1 over s plus j omega e to the 0 again is going to go to 1. So what you actually end up with is something that looks like 1 over 2j into brackets 1 over s minus j omega minus 1 over s plus j omega. Okay? To do this, now let's just sum the fractions. 1 over 2j s minus j omega s plus j omega. This looks like it's the difference of 2 squares. Alright? Okay. Then, do the division. That's s plus j omega minus s minus, because we're going to do minus times minus j omega plus j omega. Okay? S is going to cancel out. So we're going to have, so that's going to be 1 over 2j omega. Okay, so this is the difference of 2 squares. So it's going to be s squared plus j omega squared. Okay, so that's going to be s squared plus omega squared. Okay, since j is our complex function, j is minus 1. Alright, is that how we roll? Yes, it is. So that's 2j is going to cancel out, and we're going to end up with the Laplace transform of sine omega t, sine omega t is equal to omega over s squared plus omega squared. Ooh. Really fantastic stuff. So it's the same thing that you're going to do when you're solving, when you want to evaluate that of cosine. Okay, because if you have cos omega t, the Laplace identity is going to be 1 over 2 e to the j omega plus e to the negative j omega. Okay, so if you were to evaluate that, of course, this is the format we're going to use, and it's going to be s over s squared plus omega squared. So you can see how really simple and practical it is to evaluate the Laplace transform of functions. So I think we have one more. We have one more. That's of the unit function before we go into the derivative identity. You're not going to believe how simple this is. Unit function, alright? 0 to infinity, u of t e to the minus st dt. What is the unit function? The unit step function, okay, has a value of 0 for t less than 0 and has a value of 1 for t greater than or equal to 0. What does that mean? Our u of t, since we're integrating from 0 to infinity, is going to be exactly the same as 0 to infinity of 1 times e to the negative st dt. Same as integrating 0 to infinity e to negative st dt. And that means Laplace of u of t is 1 over s. We've established that. Okay, just so you don't get confused. This is practically the reason why, you know how we did the Laplace of sine omega t? You usually see sine omega t u of t. Okay, because when we're working in the time domain, our functions have to be stepped. We have to know when they come alive with the unit step function. That's what we use this for. Okay, so it has no effect on evaluating the Laplace transform. They just know it tells in time domain, it tells us when it's coming on, when it's coming off. In frequency domain, it has literally no effect. We're almost done. That's pretty amazing. Last thing we're going to do now is the derivative property. What's the derivative property? Say you have a function f of t. This is really important. It's going to come in handy when we want to solve questions, with current and voltage. Say we have a function f of t. Okay? The Laplace of f of t is going to be capital F of s. That's pretty amazing. That's not settled. But what happens when you want to evaluate the Laplace of f prime of t? Okay, how do we do that? We have a function. We know the function. We know the Laplace of the function. What do we do when we want to evaluate the derivative? Evaluate the Laplace of the derivative of that function. It's pretty really, really fun math. Let's get to work. So the Laplace of f prime of t. Okay, let me sub in the fraction so we can get a little df dt. Okay. All right. We know how it's done. Throw everything into our integral. 0 to infinity df dt e to the negative st dt. Integration by parts. Ru, okay, is going to be e to the negative st. Okay. Rdu is going to be differentiating that negative 1 over s e to the negative st. dv is everything that's left. I believe that's df dt times dt. Okay, so that's df dt times dt. Okay, and then v is going to be the integration of a differentiation. That's the function. So that's f as a function of time. This probably wasn't the clearest way to write this. Pardon me. Okay. U is e to the negative st du negative 1 over s e to the negative st. Okay. dv is df dt. Therefore, v is f as a function of time. Throw this bad guy inside. So that's going to be, recall it's going to be uv minus integral v du. Okay. Throw this back in. What's u? E to the negative st. What's v f of t? Okay, so that's f of t. E to the negative st. Now we're going to take our limits from 0 to infinity. Okay, and subtract from that our integral. Open our integral. 0, infinity, v. What's v? F of t. What's du? Negative 1 over s e to the negative st dt. Something really fantastic is about to happen now. We have to evaluate the first half. Okay, finding the limit of, let me do this over here. I want to find f of t. Where? I want to find f of t e to the minus st from infinity to 0. What do we do? E to the negative s times t. As t tends to infinity, that first half is going to be what? 0. Okay, so we're just going to be left with 0 minus f of t e to the negative s times 0. I believe that's just going to be 0 minus f. Okay, t tends to 0, so this is going to become 0 too. E to the negative s0 is going to be 0, so it's 0 minus f of 0. So that's minus f of 0. F of 0 is the value of the function at time equals 0. Okay, so we have negative f of 0 minus, evaluate this integral. What happened? Oh, this is f. Pardon my handwriting. What happened if we bring out minus 1 over s? Okay, so minus 1 over s, 0 to infinity, f of t e to the minus st dt. Does this look familiar? Does it? It should. Okay, because what you have here is the Laplace transform of f of t, which is crazy because we got there from just evaluating by partial fractions. Okay, this minus is going to cancel out, so we have minus f. Let's take this. So this is going to be minus f, so that's minus f naught, minus f of 0 plus 1 over s. Oh, something sushi. Minus s e t. Okay, I made a mistake in my differentiation here. Apologies. Okay, u is e to the negative st. Du is minus s e to the minus st. So no need for That's a really dangerous mistake. So no need for the fraction. Okay, so that's minus s e to the minus st. Okay, so that's plus s capital F of s, which is the same as s f of s minus f naught, which is the derivative, which is the Laplace transform of a derivative. If you have f as a function of time, I want to find the, let me write this out. So therefore, Laplace transform of f prime of t is going to be s capital F of s, that's s times the Laplace of f of t, minus the value of f of t at time equals 0. Really simple, really amazing mathematics. Very, very quickly, let's see what happens. Let's see what happens when you try to work out an example. So let's say f of t is equal to t. Okay? F of t is equal to t. F of 0 is, 0. F prime of t is what? 1. Alright, so let's say we want to find the Laplace transform of 1. No, we've done that before. We did that in the earlier video, you can check back. Let's say we want to find the Laplace transform of 1, but using the derivative property. So that's going to be L times f prime of t is going to be s times capital F of s. Alright, so that's Laplace transform of, f prime of t, s times capital F of s, s times 1 over s squared. Okay, because remember we did, that's for t, 1 over s squared minus 0, because f prime of 0 is, sf of s minus f naught. Okay, f naught is 0 since we're subbing 0 for time. Sf of s is s times 1 over s squared. Okay, so that's going to be s over s squared, which is 1 over s, which is the exact same thing we got when we found the Laplace transform of 1. So there you have it actually. Laplace transform is really, really simple, elegant way of solving differential equations algebraically. Because every time we had a derivative, you literally had df dt, and it became something entirely algebraic, which is pretty amazing. So when we get into solving equations as applied to circuit theory, you see how elegant and how useful this becomes.